How far do you think your powers of variable substitution go? Get out a piece of paper and feel free to follow along as I talk you through this integral. If you're new here, this is Watch Me Do Math. I make videos like these every Sunday on maths, physics, or other topics that interest me. If that sounds like your thing, be sure to subscribe and share some videos you like with your friends. So let's get into this. So this integral was from a bunch of step specimen questions I was doing, the step being the 6th term examination paper run by Cambridge University. Because there's a copyright notice on the step, I adapted this question. Firstly, it's an indefinite integral, not a definite integral, and I've changed the thing we're integrating slightly, but the fundamental way you do it is quite similar. So the reason I did this video is because I thought it was a really cool question. Basically, that's it. So where do we start with this? I've told you already that the technique we're going to be using mainly is a variable substitution, and it might be the u-substitution that you're familiar with if you've started learning about that in school, or it might be trig substitution, which is basically an extension of the ideas you use in u-substitution that allow you to use trigonometric functions and their identities to make things more convenient to integrate. But anyways, more on that later. Let's actually get into it. The first thing I noticed when I saw this kind of integral was that there was an x plus 1 here, and what looks similar to x plus 1 squared, x plus 1 squared being x squared plus 2x plus 1, inside this square root. So it seemed like you had something, and then something similar to this something squared in a square root. So this probably would look similar to x plus 1 way off in the distance, or something like that. But anyway, I knew those two polynomials were related somehow, probably through that way. So my first instinct was to change the quadratic in the square root here into completed square form. And by the way, if you are following along this video with some integration of your own, be sure to pause the video and try it yourself if you want to use this as a form of studying. So let's continue. I knew that I wanted to complete the square, change this into completed square form so that perhaps I could make u equal to x plus 1, and I wouldn't need to change the dx in any way. This would just become du directly, because the differential of, like, if you have u equals x plus 1 and you differentiate both sides with respect to x, you get du over dx is 1, or du is equal to dx. The infinitesimal change in u to be summed up is equal to the infinitesimal change in x to be summed up. And that was a useful thing for me, because it made this kind of substitution very easy. So let's put this with the square root term in completed square form, letting u equals x plus 1 as our first layer of u-substitution, or variable substitution. So naturally, that x plus 1 bracket term on the left side of the denominator just goes to u, whereas this thing inside here, well, we can rewrite it as x squared plus 2x plus 1 minus 4. And then this is du, because I've shown down here that du by dx is 1. This x squared plus 2x plus 1, as I mentioned, is equal to the square of x plus 1, so you get 1 over u times the square root of x plus 1 squared minus 4 du, and of course, taking the substitution we make, this becomes 1 over u times u squared minus 4, that square root, integrated with respect to u. So where do we go from here? There are various tactics you could take, and the one I chose to adopt, I'm sure you could do this with trig substitution, in the sense that you let u be equal to some trigonometric function and then integrate from there. But there was another way that I used, which will lead to the same result in the end. I just thought it was cool that there were two possible pathways you could take. So I'm going to do the first pathway out of simplicity, which is direct trig substitution, making u equal to some trig function. And the second way was just another v substitution, i.e. another layer of variable substitution with a new variable v instead of u. And so let's begin with pathway 1. For trig substitution, I'd let u be equal to something like 2 times the secant of some angle variable theta that we make up. U equals 2 sec theta, or if you're not familiar with the secant function, this is u equals 2 over cos theta, because we want to apply the identity within this sort of square root term. We want to apply the identity that sec squared theta equals 1 plus tan squared theta. The reason that I use 2 sec theta here is because if you square this 2 sec theta term, it becomes 4 sec squared theta, and when you subtract 4, this goes to 4 tan squared theta. Taking the square root of that just gives you 2 tan theta. So ultimately it's a fairly convenient way to do this. So let's try with this substitution, u equals 2 sec theta. On the one hand, you have 1 over this u becomes 2 sec theta, and within the square root, as we've shown, the square root goes to 4 secant squared theta minus 4, which is 4 tangent squared theta, and the square root of that is 2 tan theta. But this is still with respect to u. We're integrating with respect to u, du. We want to find the infinitesimal change in theta, d theta, in terms of du. Rather, we want to find du in terms of d theta and other theta-related functions so that we can replace it with a d theta to be integrating with respect to theta. So how do we do this? Well, we take the original substitution, u equals 2 sec theta, and we differentiate. So du by d theta is 2 sec theta tan theta. In fact, this differential comes from the quotient rule. So if you take y equals 2 over cosine theta, which is essentially what 2 sec theta is, your u is 2, u prime is 0, v is cos theta, v prime is minus sine theta, and it's u prime v minus uv prime all over v squared, which is sine squared theta on the bottom, or I mean cos squared theta on the bottom, because it's all over v squared, and then u prime v, 0 times cos theta, minus uv prime, so minus 2 times minus sine theta becomes positive 2 sine theta, so it's 2 sine theta over cos squared theta, or 2 sine over cos, 1 over cos, if you break it into these two factors, or sine theta, cos theta, cos theta. If you break it into these two factors, which becomes 2 tan theta sec theta, or 2 tan theta times secant theta, this differential here. So if you multiply both sides by the infinitesimally small change in theta d theta, then you'll get du equals 2 sec theta tan theta d theta. And that, okay, that is actually insane. I wasn't expecting that, because now it looks like this integral has been simplified by an insane amount. Because the other way I did it, it's actually interesting to reflect on this, because the other way I did it when I originally faced this question, I used a much more roundabout way, and it led me to something like integrating 1 over x squared plus 4, and that becomes, I think, a arctan of x over 2 or something like that, or 1 over 2 times arctan x over 2. But anyways, that aside, it seems like this step 1, or this first possible path, which I didn't try before, is actually much faster and much more efficient. So I guess that's something you can learn by approaching problems you've done previously and attempting to solve them in a different way. You might learn faster ways to do things. So anyway, back to actually solving the integral, you get the integral of 1 over 2 sec theta 2 tan theta du is equal to the integral of 2 sec theta tan theta d theta over, and then these two factors of 2 multiplied to become 4 sec theta tan theta. So naturally, the reason I was so happy when I saw this expression for what du is because all of the trigonometric functions cancel out. So sec theta cancels sec theta cancels tan theta, and you're just left with the integral of 1 over 2 with respect to theta, which is theta over 2 plus c. So all that's left for us to do now, actually, is to try and put theta over 2 plus c in terms of x. So if u is 2 over cos theta, u is 2 over cos theta, that means cos theta is 2 over u, or it's cos theta is 2 over x plus 1, and to take the arccos of both sides would give us something in terms of x that we can use for theta, because arccos of the cosine of theta, that is the inverse cosine function, where you're putting in an output and getting the angle that was input into the function. Arccos of cos of theta is just x, and on the other side we have, it's just theta, and on the other side we have arccos of 2 over x plus 1. So arccos of cos of theta equals arccos of 2 over x plus 1, as I mentioned, and you get theta is arc cosine 2 over x plus 1. And of course that's divided by 2 plus c to get the final integral. Okay, so that was actually, when I started recording this video, I thought it would take a lot longer because I thought the method you needed to use to solve this integral was actually pretty insane. But, of course, it's not, as we've discovered. It's fairly easy. So, I don't know what to tell you. I'm surprised myself at how easy this integral turned out to be. So, this is one solution that we've arrived at. Let's try and find another solution using that other method that I did. Alright, so how would we go about this? I'm just gonna clear the board. Alright, and we're back. And okay, so that, I'm still in shock over what I've realized about this integral. But anyways, let's try using another method that I sort of worked up myself. So the method that I used initially when I was tackling this integral in the context of using the step question as a sort of practice for myself was to do another variable substitution, letting a new variable v squared equals u squared minus 4. And the reason I wanted to do that is because I wanted to get rid of the minus 4 within the square root sign here. Although, obviously, now I see, this was a minus 3 in the original question, but naturally now I see how it could have been made much easier. But anyways, let's say we take the substitution, let's see where it leads us. It may lead us to a different solution than the 1 over 2 arccos 2 over x plus 1 plus c that we got from the previous evaluation. And by the way, if you do notice any mistakes in my working, feel free to comment, and I'd be incredibly grateful if you do. So, say v squared is u squared minus 4. If we differentiate with respect to v, for instance, because we're trying to find the relationship between du and dv, the infinitesimally small changes in the variables of u and v respectively, we differentiate with respect to u, for instance, and through the rules of implicit differentiation, v is sort of a kind of chain rule variable that we're using. So you differentiate with respect to v and then multiply by dv by du. So 2v dv by du equals 2u, and then 2v dv equals 2u du. So that's quite interesting. It shows that the infinitesimal change in each is the same, And that would be because these functions only differ by a constant. But the thing is, there's no 2u du term on top of this integral. There's no way we can substitute v in if we don't have that, because it's not easy to get to 2v dv from this situation. So what do? Well, we put a u there. How do we do that? We multiply by u over u, which is equivalent to 1. By multiplying by 1 in this way, using sort of some variable expression over the same variable expression, you can change an integral in a way that makes it easier to integrate, while not actually changing the value of the thing you're integrating. And that's something quite beautiful about integration techniques, is that you can pick whatever you like to be multiplied into an integral on both the numerator and the denominator. And it'll work. And that's something pretty awesome. At least that's how I feel about it. Integration can be a pretty beautiful thing. You have to use a lot of creativity as opposed to differentiation, which is more about the application of the rules for differentiation that we've worked out over the years. So anyway, if you multiply both sides by this fraction u over u, you get the integral of, or maybe 2u over 2u, because we want 2u on the top. We get 2u over 2u squared times the square root of u squared minus 4 du. And this 2u du is 2v dv, as I said earlier. This v squared is u squared minus 4, and u squared is v squared plus 4. So we get the integral of 2v dv over v squared plus 4, 2v squared plus 4, times root v squared. And these factors of 2 cancel out, and this root v squared becomes a v, which cancels out with this v here, and we're just left with the integral with respect to v of v squared plus 4. And this is sort of the form that I reached in my own first attempt at this kind of problem. And for those of you with the background knowledge to make this insight, you may recognize it as similar to the integral, similar to the differential of arctan x. Traditionally, it's a standard integral that people are sort of expected to know at a certain level of maths. The fact that 1 over x squared plus 1 dx integrates to arctan x. And it's fairly helpful in figuring stuff out when you reach a form like this, with the infinitesimal change over something squared plus something. But the thing is, how do we apply it to this situation with the plus 4? Well, that's the thing. You can try and use another variable. So we're going to substitute yet again. Suppose we take w is, or 2w is v, because if we put 2w in here, this will become 4w squared. And we can factorize stuff out such that we get, or maybe not 2w. Wait, give me a sec. Okay, I'm back after some thinking, and we're not going to do another variable substitution. In fact, we are going to be able to do something by inspection, if I can delete this. Right, so what we're going to do here, with our knowledge that this eventually goes to arctan x, I'm going to explain to you why it is going to arctan x. I'm going to tell you how we can reach a similar conclusion about this integral of 1 over v squared plus 4 with respect to v. So, the first thing I'm going to do is multiply out by 2 over 2 and move the 1 over 2 factor outside the integral so that the inside is multiplied by 2, if that makes sense. So basically I'm transforming this integral to 1 over 2 times 2 over v squared plus 4 dv. So why do I do this? Well, okay, so here's the thing. If you're not familiar with the technique I'm about to use, my tablet, my pen tablet. Okay, it seems to be that my USB cable connecting my pen tablet to my computer often refuses to work if I touch it the wrong way. So anyways, if you're not familiar with the technique I'm about to use, you will probably become familiar with it once you learn the differentials of these various arc something functions, because it's the same technique that you use to differentiate it that you can use to integrate, or it's the same sort of model of thinking. The thing you need to visualize in your head is the same, essentially. So, take this triangle, for instance. Okay? So this is a triangle that I'm going to create. It's a completely fictional triangle, but it's going to help us visualize how different trigonometric functions are related, because the last substitution we're going to pull here is a trig substitution, in the sense that something is going to be made equal to some trigonometric function. So, suppose you have some angle theta here, and one side of this triangle is a side of length 2, and one side is a side of length v. By Pythagoras' theorem, this hypotenuse should be v squared plus 4, or the square root of v squared plus 4. Right. So because of the way we've drawn this triangle, tan of this angle theta is going to be v over 2. Tan theta is v over 2. So say we want to differentiate tan theta with respect to v. How would we do that? Or perhaps we don't want to differentiate tan theta itself, but we want to get a substitution out of this that we can use. So we know that theta is going to be arctan of v over 2, and that's a fact that'll be useful to us later. But for now, let's just think upon this. Tan theta is v over 2. If you differentiate with respect to v, this side becomes 1 over 2, whereas this side, through the chain rule, becomes d theta by dv times the differential of tan theta with respect to theta, which is secant squared theta. And that's something you can arrive at through the same method of using the quotient rule as I did to arrive at the differential of secant theta with respect to theta. So d theta by dv, secant squared theta, is equal to 1 over 2. Or d theta by dv of 1 over cos squared theta is equal to 1 over 2. So in essence, what we are trying to do here is express cos squared theta in terms of v, so that we can get a way to substitute dv along with whatever terms are necessary within the equation into terms of theta. And so I apologize if my explanation is a bit all over the place, but I'll just do the math and hopefully it makes sense. So d theta, if we multiply both sides by both dv and cos squared theta, becomes cos squared theta over 2 dv. Now, what do we do with this? The thing is, this is not a useful relationship for us to know about, because we've got dv here, but the factor it's multiplied by is in terms of theta. So what we do is we refer to our original situation, this right-angled triangle, which demonstrates all the relationships between the sine, cosine, and tangent functions, and try and find some value for cos squared theta in terms of v. So cos squared theta, cos is the adjacent side over the hypotenuse. And the adjacent side here, 2 theta, is 2. And the hypotenuse is the square root of v squared plus 4. You may be seeing where this is going. You may see where this is going, indeed. So if you were to square cos theta, so cos squared theta, you'd get 2 squared on the numerator and this square root squared on the denominator. You'd find 4 over v squared plus 4. And of course, that whole thing is divided by 2 next to dv. So this goes from 4 to 2, removing one factor of 2. So ultimately, we find out that d theta is 2 over v squared plus 4 dv. And why is that information useful? Because we are going to make the substitution theta equals arctan v over 2. So that's the cool thing about this. We don't even need to find some arctan v over 2 in our original integral just to be able to make the substitution. All we need to know is that there is a relationship between these two variables that can be used to express this integral in terms of v, in terms of d theta, even if it's not explicitly in terms of theta, if that makes sense. So, while typically you might do something like u equals some complicated function of x that you found as well as its derivative inside of the regular integral, no. We're doing this the other way around, so that there is some complicated function of v. Basically what we're doing here is v equals 2 tan theta. But the point I'm trying to make is it doesn't matter in what way you express your initial relationship that you're using for the variable substitution. You can always just use that relationship to find what certain expressions are in terms of other expressions, as long as you know the key link between those two variables. So this relationship, v is 2 tan theta, I never have to explicitly substitute 2 tan theta into v here, but I can just do some other stuff with the information that I get from that relationship and still make the substitution work. So perhaps this was an overcomplicated way of doing it, but the insight should still be helpful to those of you who are interested in this kind of integration technique, right? So anyways, if d theta is equivalent to basically the entire integrand, then we can just find that this integral is 1 over 2 times the integral of d theta, which is 1 over 2 times theta plus c, or, knowing that theta is arctan v over 2, 1 over 2 arctan v over 2 plus c. So hopefully that's coming up properly on the screen. Oh no, it isn't. But anyways, if we were to write this out again, the integral, I, is 1 over 2 arctan v over 2 plus c. And you can go through all the tedious variable substitution steps to get back to your original form. So knowing that v squared equals u squared minus 4, v is the root of u squared minus 4, and this becomes 1 over 2 arctan the square root of u squared minus 4 over 2 plus c, and again, knowing that u equals x plus 1, this x plus 1 squared minus 4 becomes that square root in the original sort of status of our fraction, 1 over 2 arctan x squared plus 2x minus 3 over 2 plus c. So that's the interesting thing. You can integrate something 2 different ways and get 2 different results. The other answer that we got for this integral was, it was 1 over 2 arccos (2 over x plus 1 plus c). And that's not to say that these expressions are equivalent, because the only thing you can actually say about these expressions is that if you take this to be sort of one version of the integral, and this to be another version of the integral, their definite integrals will be the same because the area under the original function will be the same. But that's not to say that these 2 expressions are always equal to one another. It's only to say that the definite integrals will be the same. That's all you can say when you integrate something and get two of the same function. So this is not necessarily true. They're not equal to each other. Hopefully that insight is passed along to you. But you can say that f1 of b minus f1 of a will be equal to f2 of b minus f2 of a because they have the same geometric meaning. So that's basically all I wanted to say for this integral. And just on cue, my pen tablet has broken again. So hopefully you enjoyed watching this video. If you found the integral and the stuff behind it interesting, then be sure to subscribe and leave a comment if you found that there's anything else you want to discuss, or email me at watchmedomath@gmail.com. So until next time, thank you for watching.